Hi everyone, I am Dr. Moksha Satya, working as an assistant professor in Aditya Silver Oak Institute of Technology, Silver Oak University. This is my third lecture on matrices and which is in a syllabus of semester 1. Today I am going to cover rank of a matrix and inverse of a matrix. Let's start with the rank of matrix. The positive integer R is said to be rank of a matrix A if it possesses the following properties. The first property is there is at least one minor of order R which is non-zero. And the second, every minor of order greater than R is 0. The rank of matrix A is denoted by row A. Here, the rank of matrix says there are many minors according to the number of elements, but the maximum minor which is non-zero is of order R, then and only then the rank of a matrix is R. Note that the rank of matrix remains unchanged by element transformation. Also, the rank of product of two matrices cannot exceed the rank of either matrix. That means if I multiply matrix A and B, the rank of matrix A will not exceed rank of A and rank of B. In a symbolic, we can write rank of AB is less than or equals to rank of A, or rank of AB is less than or equals to rank of B. Now, using this row echelon form which we have learned earlier lecture, we can find rank of matrix. The rank of matrix in a row echelon form is equals to the number of non-zero row of a matrix. Means there is a matrix given, we can change that matrix into row echelon form and we can say from that row echelon form what is the rank of matrix. For that we need to identify the number of non-zero rows. That number of non-zero rows is nothing but the rank of matrix. So let's see how to find the rank of matrix. Before jumping to the example, let's recall the row echelon form. Row echelon form has three conditions. First one, every zero row should be at the bottom. The second, every non-zero row should have leading one. And the last, third, every row which has a leading one should be at the right for the preceding row. So, keeping this in the mind, let's start for the example of rank of matrix. Here is the first example. Let's give it a name. This matrix as A, and the matrix is 5, 3, 14, 4, 0, 1, 2, 1, 1, minus 1, 2, 0. Now, for the first row which is non-zero, we need to have the leading one. Either we can interchange the first row and the third row, which directly makes the leading one, and for the second path we can multiply first row with the 1 by 5. But I'll go with the first path, that is the interchanging first and third row. After interchanging first and third row, we'll have 1, minus 1, 2, 0, 0, 1, 2, 1, 5, 3, 14, 4 as a resultant matrix. Now we need zeros in the bottom of leading one. We have already 1 0 in a second row, so we do not need to change that 0. Only we need to change is 0 in a place of 5, and that's why we will apply the operation R3 minus 5R2. Multiplying R1 with the minus 5 will have minus 5, 5, minus 10 and 0. Adding these to the third row, which is 5, 3, 14, 0 gives 0, 8, 4 and 4. Now you can see here we have leading 1 in a second row, and that's why we will apply this operation R3 minus 8R2 to make the below element of that leading one 0, which is 8. So apply minus 8 means multiply minus 8 to the row R2 and adding this to the R3 will have change in R3 row, which will be 0, 0, minus 12 and 4. Now again, to make this matrix in a row echelon form, we need to make leading one in a third row, as this third row is a non-zero row. So let's multiply R3 by minus 1 by 12. After multiplying R3 by minus 1 by 12, we'll have third row as 0, 0, 1 and 1 by 3. Now let's check whether this is in a row echelon form or not. Here each and every row is a non-zero row. That's why there is no case of zero row in the bottom of this matrix. Now every non-zero row should have leading one. Yes, we have 3 leading one. So also check whether this leading one satisfies the condition 3, that it should not be in a left hand side. Yes, it is not in a left hand side, it is in a right side, and that's why it also satisfies the condition number 3. So this matrix in a row echelon form. That's why moving to the answer, we have the equivalent matrix in a row echelon form, and that's why the number of rows will be the rank of matrix. Here the number of rows are 3, and that's why the rank of matrix is 3. That's why row of A is 3. So moving to the example 2, here is the matrix 1, 2, 3, minus 1, minus 2, minus 1, minus 3, minus 1, 1, 0, 1, 1 and 0, 1, 1, minus 1. To make this matrix in a row echelon form, we need to have leading element for each and every non-zero rows. First row is non-zero row, that's why we need to have leading one in a first row. Here the first non-zero element of that row is 1. That's why that 1 is leading 1. Now we need to make zeros below that leading 1, 0. So for this we have second, third and fourth row. But in a fourth row we have already our first element as a 0, 1. That's why we have only 2 job left, which is to make minus 2 and 1, 0. For this, we need to apply 2 operations. The first operation will be multiplying first row with the 2 and adding in a second row. And the second operation will be the directly that the first row will be subtracted from the row 3. So, the 2 operations will be R2 plus 2R1, R3 minus R1. For the first operation, we need to multiply first row with the 2, which makes 2, 4, 6 minus 2, and adding this to the second row will have second row as 0, 3, 3 minus 3. Now for the second operation, subtracting R1 from the R3 will have R3 as 0, minus 2 and 2. And the fourth row will remain same as 0, 1, 1 minus 1. Now second row is our non-zero row. That's why we need a leading one there. For making that row leading one sufficient, we can interchange second and fourth row. That's why let's have operation R24, which makes the matrix like this. Now we have leading one in second row, which is in a second column. So that's why column and the third row, fourth row, intersection of that elements, we have 0 instead of minus 2 and 3. For this, we'll multiply, we'll apply operations R2 plus 2R, R3 plus 2R2, R4 minus 3R2 will change R3 and R4. So the change R3, R4 will be 0, 0, 0, 0, 0, 0, which makes bottom two rows 0 row, and which is also satisfy the condition 1 of row echelon form, that each and every row which is 0 row should be at the bottom of the matrix, and it is in the bottom of a matrix. Now this makes this matrix in a row echelon form as non-zero row have leading 1 and that leading 1 have zeros below that column. So, leading to the answer will have equivalent matrix in an echelon form, and the number of non-zero row of this echelon form is 2. Other 2 is 0 rows, and that's why the rank of matrix is 2. Now, next is the inverse of a matrix. Here, we'll find inverse of matrix using Gauss-Jordan method. So, for that, we need to take matrix A, any non-zero matrix. Now we know if we multiply any matrix with the identity matrix, we'll have that matrix again. So using that condition, we'll have A is equals to IA. So using this, we'll find the inverse of matrix. For this, we need to apply suitable elementary row operations, row transformations to A on the left hand side and to I on the right hand side of a matrix A to reduce as the identity matrix, which will convert identity matrix in any other matrix, say B. So we'll have resultant one, that is I is equals to BA. As we have converted A into identity matrix, and I will be converted into any other matrix as we have applied elementary row operations to the left hand side and right hand side of the our equation A is equals to IA. Now using this, I is equals to BA, making B as a subject form, will have B is equals to A inverse. That's why in this Gauss-Jordan method, if we apply to elementary row transformation to A is equals to IA and converting A into I, and I will be another matrix, that another matrix B is nothing but our A inverse. So now let's find the inverse of following matrix by elementary row transformation, which is none other than Gauss-Jordan method. Now let's see the example 1. For that, we'll have a matrix 2, 3, 4, 4, 3, 1, 1, 2, 4. As we know, A is equals to IA, but here A is of order 3, and that's why I have taken identity matrix of order 3, and that's why this makes A is equals to I3A. Now putting the matrix value, means matrix, in a place of A on the left hand side and I3 on the right hand side, will have 2, 3, 4, 4, 3, 1, 1, 2, 4 is equals to 1, 0, 0, 0, 1, 0, 0, 0, 1 into A. Now let's make left hand side matrix in an identity form. Now whatever we multiply, subtract, and whatever we do on a left hand side, it will convert it, it will reflect it directly on a right hand side, and that's why if we change the matrix A, which is of a on the left hand side, it will change the matrix I3 on the right hand side. That's why let's try to make this matrix A in a reduced row echelon form. For that, we need to first have a row echelon form. For this, we need to have leading 1 in the place of 2, which is a intersection of first row, first column, means A1 1 element. But we can see there is one element 1 in a first column, which is of row 3. That's why let's interchange first row and the third row. So R13 is the operation which will give 1 2 4 4 3 1 2 3 4 on the left hand side. The same operation will be applied, and that's why the last row, which is 0 0 1, will come in the place of row 1, and that's why the right hand side will become 0 0 1 0 1 0 and 1 1 0. Similar way, we need to have other operations. Now, to make this left-hand side matrix in a row echelon form, we need zeros in place of 4 and 2, because we need zeros in a column, in a bottom of column from the leading one. For this, let's apply the operation R2 minus 4R1 and R3 minus 2R1, which will change R2 and R3 respectively. First operation is R2 minus 4R1, and for this we need to multiply R1 with the minus 4, and we'll have minus 4, minus 8 and minus 16, and then add to the 4 3 1. In a similar manner, we need to multiply right hand side first row with the minus 4. We will become 0 0 minus 4, and it will be added to the 0 1 0, and that's why the first row will be changed for the both the sides is the second row will change from the both the side is 0 minus 5 minus 15 and 0 1 and minus 4. Same way, for the second operation R2 minus 2 R1 will change the R3 rows, which is 0 minus 1 minus 4 and 1 0 minus 2. Now for the next. Either we can interchange second and third row, yeah, we can multiply second row with the minus 1 by 5. I'll go with the second one with R2 multiplying with the minus 1 by 5, which gives changing second row, which is 0, 1, 3 on the left hand side, and on the right hand side we'll have 0, minus 1 by 5, 4 by 5. This is the resultant equation after this operation. Now this makes this one as a leading one for the row 2. Now we need to make 0 instead of this minus 1, and that's why we need to apply the operation R3 plus R2. This will change the third row itself, and which will be 0 0 minus 1 and 1 minus 1 by 5 6 by 5. So here we'll have the leading one for the both first row, and we have minus 1 in the last row. So for the leading one in the last row, we need to multiply it with the minus 1. So minus 1 R3 will give 0 0 1 minus 1 1 by 5 and 6 by 5 in both the sides for the third row. Here, the left hand side, the matrix is in a row echelon form. Okay, as there is leading one for each non-zero row, and there is no leading one appear on the left hand side for the preceding rows. Whatever we have applied on a left hand side, it has changed our right hand side also. So, for the reduced row echelon form, will go on same way. So for the reduced row echelon form, I will focus on our third leading one, which is on a third row, and make all these elements above that leading row 0. For that, we'll have operation R2 minus 3R1 and R1 minus 4R2. This operation will apply on both the sides, and the resultant equation will be 1 2 0 0 1 0 and 0 0 1, which is on the left hand side, and for the right hand side we'll have 4 minus 4 by 5 minus 19 by 5, 3 minus 4 by 5 minus 14 by 5 minus 1 1 by 5 6 by 5 into A. Now for the second row we have only one element resulting, which is not 0, and it is also above the leading one, and that's why making this 2 is a 0 will use the operation R1 minus 2R2, and that's why we'll change the first row, and which will be 1 0 0 for the left hand side, and for the right hand side minus 2 4 by 5 9 by 5. Other two row will be the same. So you can say on the left hand side we'll have the reduced row echelon form, which is nothing but our identity matrix of order 3, and that's why we have reached to the last stage of a Gauss-Jordan method, that is I3 equals to BA, where B is nothing but our A inverse, and that's why A inverse will be this matrix. So as an answer, I have A inverse as minus 2, 4 by 5, 9 by 5, 3, minus 4 by 5, minus 14 by 5, minus 1, 1 by 5 and 6 by 5. Now I can take out 1 by 5 common from the matrix and will have other 1 by 5 minus 10, 4, 9, 15 minus 4 minus 14 minus 5, 1 and 6 as our A inverse. So let's see the second example. Here we have matrix A as 1 minus 1 0 2 0 1 1 minus 1 2 1 2 1 and 3 minus 2 1 6. Here the matrix is of order 4, and that's why we'll have identity matrix of order 4. That's why we have A is equals to I4A. Now putting the matrix in a place of A and I4, A for the left hand side and I4 for the right hand side, it will have like this. Now for the Gauss-Jordan method, we need to have identity matrix. That means the reduced row echelon form of a matrix given on a left hand side. So let's reduce the matrix A to the reduced row echelon form. For this, first we'll need this operation R3 minus R2 R1 and R4 minus 3 R1, because we already have leading one in our first place of first row and first column. So we'll have this matrix 1 minus 1 0 2 0 1 1 minus 1 0 3 2 minus 3 and 0 1 1 0 on the left hand side, and similar changes will happen on the right hand side, that is 1 0 0 0 0 1 0 0 minus 2 0 1 0 and minus 3 0 0 1. Now we already have the leading one in a second row, second column, and that's why we need to make this 2 as a 0. For this, we need an operation R3 minus 2 R1, sorry, R3 minus 3 R2 and R4 minus R2. And the matrix will change only for the R3 and R4. So R3 will be 0, 0, minus 1, 0 for the left hand side, and for the right hand side we'll have minus 2, minus 3, 1, 0. And for R4, left hand side will have 0, 0, 0, 1, and for the right hand side we'll have minus 3, minus 1, 0, 1. We have here, you can see we have minus 1 in a place of first non-zero element which is on a place of leading one, and that's why we'll multiply -1 with the R3. And you can also see that there is already leading 1 in row 4. That's why we need not to do anything for the row 4. So the operation -1 R3 will change the third row by 0, 0, 1, 0 left hand side, and for the right hand side we'll have 2, 3, -1, 0. Now the left hand side matrix is already in a row echelon form, and to convert that matrix into reduced row echelon form we need to focus on our leading one. So let's starting with this, the last leading one will make all other element 0 in that column, but in a third row it is already 0. That's why we'll focus on R1 and R2 only, and the operation will be R2 plus R4 and R1 minus 2 R4. We'll change first and second row by 1 minus 1 0 0, 0 1 1 0 respectively for the left hand side, and the for right hand side will have 7 2 0 minus 2 minus 3 0 0 1. Now making focus with this leading one, we need to change this one as a 0, and that's why we have this operation R2 minus R3 will change the R2 by 0 1 0 0 for the left hand side, and for the right hand side it will change by -5 -3 1 1. Last but not the least operation will be for this -1 to make this as a 0. We'll add R1 plus R2, and the resultant R1 will be 1 0 0 0, and the for right hand side 2 minus 1 1 minus 1. In the left hand side we can see there is an identity matrix of order 4. That's why we have achieved our Gauss-Jordan method for the inverse matrix. We have right hand side one matrix which is B, and that's why I4 is equals to A inverse into A. As we know, this matrix B is nothing but our A inverse, and that's why A inverse is 2 minus 1 1 minus 1 minus 5 minus 3 1 1, 2 3 minus 1 0 minus 3 minus 1 0 1. And here we are at the end of this lecture, and to summarize this, let's recall what we have done today. We have find the rank of matrix and inverse of matrix using row echelon form and reduced row echelon form. For the row rank of matrix, we only need row echelon form, and the non-zero row of that row echelon form will be the rank of matrix. And for the inverse, we have Gauss-Jordan method, and we need to change the matrix into reduced row echelon form with the specific equation which is A equals to IA. This operation will change I, and the resultant matrix which will be changed from I will be A inverse. And that's all for today. Thank you.